We're going to revisit inverse trig functions because in the next couple of lessons we're going to have to deal with their derivatives and their antiderivatives. So this is just straightforwardly kind of a review on inverse, sine, cosine, secant, and tangent for sure. So we know from our work in trig that the sine and cosine function, they're continuous functions, they're periodic functions, they have repeated behavior in the plane. So we know that if we're going to talk about their inverses, then we're going to have a problem when it comes time to reflect that inverse function in the plane over the line y equals x, because it will not pass a vertical line test, therefore we can't talk about it being a function. So we were forced to restrict the domain of those two periodic functions and only look at a small part of the domain in order to have a valid discussion about them having an inverse. So here is a piece of the parent function y equals sine of x. We've restricted the domain to negative pi over 2 to positive pi over 2. Now this is not the only place in the plane that we could talk about the sine function having an inverse. But remember, what we need is we need our original function to be strictly monotonic, only increasing or only decreasing. So we could actually restrict it to pi over 2 to 3 pi over 2. We just basically need from a hill to a valley or from a valley to a hill so that we're strictly monotonic when we talk about the inverse. And we can reflect this in the plane over the line y equals x, and the result will be a function. It will pass the vertical line test. So that's what I've done here. Here's the parent function with a domain restricted to negative pi over 2 to positive pi over 2 for the sine function, and we can see here's what sine inverse looks like, and it does indeed pass the vertical line test. So just as we don't put the exponent of a trig function above the angle measure x, but we put it before the angle measure, we put the inverse notation after the trig function and before the angle measure as well here. Remember, we had a discussion that if we had this going on, mathematicians knew it would be too confusing because this could have multiple meanings. Does this mean it is the sine of the quantity x squared, or does this mean it is the quantity sine of x squared? And so mathematicians agreed that the best thing to do when this was the case is to put that before the angle measure so that we knew the whole thing was being squared. And so here we know it's the inverse of the whole sine function. And the same's true about the rest of the trig functions. We'll also see the same is true about having to restrict the domain to talk about cosine having an inverse as well. And again, as you can see, we have restricted the domain on cosine from 0 to pi. We have restricted it in a way where we go from a hill to a valley, so that cosine is a piece of cosine that is strictly monotonic. It's decreasing everywhere, and we can indeed reflect that piece over the line in the plane y equals x, like the inverse function will do, and we can talk about cosine inverse. Now, cosine inverse has a domain and range issue that are, remember, connected to cosine. So recall from trig that x is the angle measure, y is the real number value of the trig ratio of the adjacent side over the hypotenuse, specifically in cosine. Conversely, with the inverse, we can begin with the real number value of the trig ratio, we'll call it y, and find the angle measure for which the real number value is true. And we'll talk more about that when I give you some hints later on. So you'll definitely need to know the inverse function for sine and cosine. You'll need to know it as well for tangent and for secant. So remember, if the sine of an angle measure is a side ratio, then the sine inverse of the side ratio has to equal the angle measure, because these two functions undo each other. So if I start with a function machine and I feed it a theta, and that function machine takes the sine of whatever I feed it, then it's going to yield me a side ratio. If I take that same side ratio and feed it into the function machine that reverses the operation of taking the sine, then it maps me back to where I started, to my original domain value of theta. So just remember that. That's true for all of these inverse trig functions. So let's take a quick look at inverse tangent. If we restrict its domain from negative pi over 2 to positive pi over 2, that's just one piece of the infinitely many pieces of the tangent function, because remember, we have vertical asymptotes every pi in the plane, and so we just take that first little piece that's right at the origin. When we reflect it over the line y equals x in the plane, we can see that tangent inverse is a smooth continuous function. Its domain is all real numbers, but its range is negative pi over 2 to positive pi over 2. So all of the relationships that we know between a function and its inverse are still true in the trig setting. So there's an equivalent way to determine the inverse of cotangent and cosecant, but because they don't play a significant role in the AP Calc exam, we don't explore them here. All right, and finally here is the inverse secant. Now secant's kind of strange. It has a vertical asymptote at pi over 2. The secant function does. And remember, we need to be strictly monotonic, so we need to be increasing everywhere or decreasing everywhere if we want to talk about having an inverse. So I know it seems kind of odd that we restrict the domain with that vertical asymptote right in the slap dab middle of it, but it's a way to restrict the domain of secant so that both pieces are strictly monotonic. This is increasing everywhere on this domain. And so we can reflect those pieces over the line y equals x in the plane. This piece reflects up here, this piece reflects right here. So the blue graph is actually the graph of secant inverse. All right? Prefix arc is used quite a bit for trig inverse functions. It doesn't change the behavior or the definitions of the functions we just looked at. It's just alternate notation. So if you see something that says the arc secant of x, you can equivalently write that as the secant inverse of x. Those are equivalent. That's just notation difference there. All right, so here's some helpful info. You know all this info. Again, this is just kind of sort of a review. Most calculators don't have a secant, cosecant, or cotangent button. So if you need those values, remember these reciprocal relationships. If you need the secant of an angle measure, then in your calculator find the 1 over cosine of that same angle measure. Cosecant is 1 over sine, cotangent is 1 over tangent. Please remember the Pythagorean theorem identity. Anytime you see sine squared plus cosine squared of the same angle measure, then you can replace that with a value of 1. This is important because when we're doing inverse work, it's important to remember this is what's going on. If the sine, cosine, tangent, secant, whatever, of an angle measure gives us a side ratio, then the inverse of that trig function, the inverse of the side ratio, should map us back to the angle measure. Here's the domain values for the regular trig function, and they lead to range values. And remember, inverse functions reverse those relationships so we get mapped back to where we started. The only thing that I would kind of warn you about, it's not a true statement that the inverse functions carry this reciprocal relationship. So be careful of that and don't use that. So let's do some examples here of trig inverses. So determine the value of tan inverse of -1. And to me, the easiest way to do these is I realize that that's going to be an angle measure. What angle measure does the tan inverse of -1 equal? So I try to remember that I'm looking for the angle measure where tangent was equal to -1. And so, you know, a lot of this is back to the unit circle work. I remember at pi over 4, my sine and my cosine have the same magnitude, that kind of root 2 over 2, root 2 over 2 thing. And I remember in quadrant 1 and in quadrant 3, since sine and cosine have the same sine, SIGN sine, that tangent was positive 1. But in quadrant 2 and in quadrant 4, sine and cosine are going to have different SIGN signs, and so at iterations of pi over 4, for those angle measures, tangent should equal -1. So this is 1 pi over 4, 2 pi over 4, so that's true at 3 pi over 4, and it's also going to be true at 4, 5, 6, 7 pi over 4. All right, so these are not going to be difficult. We've done this work before. Determine the value of the following inverse trig function. So again, this is what I tell my brain. For what angle measures does the sine have output values of 1/2? Shorter of the two values, 1/2 or √3/2. So that's going to happen at pi over 6. That's a positive 1/2. It's also going to happen at 5 pi over 6. Okay, so that's where the sine value is going to be a positive 1/2. I don't have it written here, but you can see I'm staying within theta measures of 0 to 2 pi. Give A equals the tan inverse of 3/4, or given A equals the tan inverse of 3 over 4. Find the sine of A, the cosine of A, the cotangent of A, secant of A, and cosecant of A. And this is what we're talking about. We're talking about if we have an angle measure alpha, and we know that the tangent inverse is 3 over 4, then we want to find the sine of alpha, right? And we recognize that the tangent of alpha would have to be 3 over 4. We know that tangent is opposite over adjacent. So I know I have a y value of 3 and an x value of 4, and I have labeled my triangle that way. This allows me to find the sine of alpha. Here, the hypotenuse is just called c, so that's what we'll do. The sine of alpha is 3 over c. The cosine of alpha is 4 over c. The tangent of alpha, which it didn't ask for, sorry about that. The cotangent of alpha, which it asked for, is going to be 4 over 3. The secant of alpha is going to be c over 4, and the cosecant of alpha is going to be, here we are, c over 3. All right? So again, given alpha is the tangent inverse of 1 minus x, find the sine of alpha, cosine of alpha, and so forth. So same kind of thing going on here. We know that this is 1 minus x over 1. We know that this is opposite, this is adjacent. So we've labeled it that way. So the sine of alpha is 1 minus x over c. The cosine of alpha, and yes, we could put c in terms of x using the Pythagorean identity. Why don't we just do that? And we could find c here as well. Okay, so we know that c squared has to equal 1 squared plus the quantity 1 minus x squared. So that is 1 plus 1 minus x squared is 1 minus 2x plus x. I write s. Plus x squared. All right, so c squared equals x squared minus 2x plus 2. So c is the square root of that, x squared minus 2x plus 2. So we could put that in for c. I'm not going to take the time to do that because you understand that. So the cosine of alpha is 1 over c. The cotangent of alpha is 1 over 1 minus x. The secant of alpha is c over 1, and the cosecant of alpha is c over quantity 1 minus x. All right, we'll stop here. We have some more examples to do in the next video.